In this work, a hierarchical and robust framework for learning bipedal locomotion is presented and successfully implemented on the 3D biped robot Digit. We propose a cascade structure controller that combines the high-level trajectory planning with low-level intuitive feedback regulations. The high-level learning-based policy propagates reference motion trajectories in real time at a low frequency compatible with real hardware implementation. This encourages the stability of the walking gait by modifying the reference trajectories accordingly to the reduced state of the robot. The low-level model-based regulation applies compensation to the reference trajectories at a higher frequency based on instantaneous state feedback. This feedback-based trajectory regulation compensates for uncertainty in the environment, and based on our experiment observation, it is one of the key factors leading to the effortless sim-to-real transfer. In addition, we implement a learning pipeline that considers feasible initial poses of the robot that can be implemented in hardware. For this, a standing controller is used to bring the robot to a stable pose after powering the robot up. The process is repeated to collect a set of initial states for the training process. After the training, the policy is tested in simulation, and finally the policy is tested in hardware. Here we show the training process of the policy. We denote that the walking policy is learned from scratch and does not rely on known reference trajectories. As the training progresses, we see that the policy learns stable and robust walking gaits. We demonstrate that our learning pipeline and controller structure allows to transfer the learned policy between different simulation environments and from simulation to the real robot without using randomized dynamics in training or extensive hyperparameter tuning. Experimental results on Digit show that the policy is robust against external disturbances applied to the robot in different directions, even though the policy is trained without disturbances. The limit cycle of the robot's joints show that the policy is able to recover effectively from the push as the joint limit cycle returns to a stable periodic orbit after the disturbance. To further evaluate the robustness of the learn control policy, we make Digit walk forward and backwards in various terrains with different levels of difficulty. These terrains include flat vinyl ground, mulch, flat rubber ground, and regular rubber terrain. The controller is able to adapt to any of these terrains while keeping a stable and robust walking gait. Thank you.